under a curve and the x-axis. Yesterday, you would be given something like this. This is the first one on the notes. What geometric formula will give you the area? 1/2 base times height. What is the base of this triangle in our interval 0 to 2?
2.
What is the height of it?
6.
So, what is the area of that? 6. Done. Okay, so if you are not explicitly given units, you don't need to be worried about like adding units squared. So like once we get into application of it, you'll start seeing units, but for now, like if you don't have it, that's fine. On the next one, there we have our line y equals 3 on the interval -2 to 1. So when we draw this one in, what shape is going to give us our area? Square, rectangle, whatever you want to call it. What's the base? What's the height? So what's the area? 9. The next one, step 1, change your interval so it goes from 2 to 4. Because then it's a little bit less messy. So if your interval is from 2 to 4, you would mark off your interval, find the area between. How is this one different than the other two and what you saw yesterday? There's a curve. So, options. What could you do to give this approximate area? You can make a bunch of little squares. You could guess and be like, oh, that one's about 1/3 of it, whatever. This is what we're going to be working with for the next couple days, is this idea of like, how can you approximate an area under a curve? And what we're going to base it off of is kind of what ancient Greeks did when they were working with geometry. So, area of a circle. It did not start out with pi r squared. Instead, what they did, and what everything is kind of based off of, is they took shapes that they knew, like a triangle. And they put triangles within this circle, and they found the area of the triangles, added them up. How would this approximation turn into a better approximation? You make smaller triangles. This is called the exhaustion method, because the more triangles you add in, is your approximation going to get better or worse? Better. These triangles right here, would they be an over or an under approximation? An under. How do you make it an over approximation? Yeah, have the triangles go so that when they connect, they're like connecting outside of it, so that every triangle goes a little bit outside of it. Again, if you want a better approximation, whether your triangles are inside or outside, how do you get a better approximation? You add in more triangles. So the exhaustion method is used a lot, and that's where like pi came from, because what they did is they took all these triangles and found the perimeter around those, and then it got to like 22/7, which eventually they're like, hey, this is not 22/7, but it's really, really close, things like that. So we are going to use methods like that to approximate the areas under a curve. However, for now, we are not using triangles. We are going to make rectangles. So the area of rectangles to approximate the area under curves and the x-axis. We are going to naturally go to the x-axis. These things have to be bounded somewhere. We are bounding them to the x-axis. The generic formula for the sum of the rectangular partitions just means like the sections that are rectangular, so however many rectangles you have, on the interval a to b is given by s of n, can be used to approximate the area between f of x and the x-axis. This summation formula looks super duper scary. However, if you break it up into its pieces, what does sigma mean? Sum. F of something times delta x. In practice, what this means is like all of these rectangles, in general, how do you find the area of a rectangle? Base times height. So if you look at this, f of that inner part is the height of the rectangle. And if you look at the example pictures underneath, what is the height of the rectangle going to be bounded by? What's it based off of? The curve, the function. So this is based off of the function. So that's why it's f of. It's not a for sure, this is saying f of wherever your rectangle is. So there is our height. So then delta x. Like, what does delta mean? Change in x. So what delta x ends up being is the width. And to make things simple for us, all of our widths are going to be the same. So when we make our rectangular partitions, when we make these rectangles, we're going to have all the rectangles be the same width. We're going to call that delta x. Since we want everything to be the same, the way you find delta x, so you guys have where delta x, I'm going to go to a new page. If your interval is going to run from B to A, and you're going to have n partitions, and I'm saying partitions, it's rectangles. So if I tell you that I want you to have 7 rectangles, 9 rectangles, 4 rectangles, the way you make sure that they're evenly divided is delta x is just going to equal, that should be A to B. I got ahead of myself. B minus A. So how long is your interval that you're finding the area for, divided by however many rectangles you're having. Because if you know how long it is and how many rectangles you want, this will make all of your rectangles be the same width. They're each 1 long, 2 long, 0.7 long, however long they are. So n is the number of partitions. That just means how many rectangles you're going to have. Today we're going to look at 3 types of rectangles. So this first one, these are called right endpoint rectangles. You might want to like darken up your picture if you can't see it very well. So these rectangles, if you look at them, why would they be called right endpoint rectangles? Yeah, they hit on the right side. So right endpoint rectangles mean when you make your rectangle, it is hitting on the right side. So the right side of it is going to distinguish the height of it. Down here at the bottom, do you see how all of these widths look the same? Each of those individual widths, that is your like delta x. Like how wide is it? It's the change in x. So each change in x you take over, each width you go over is going to bring you another rectangle. The next one in your little box is called a left endpoint. Do we still have our delta x? Are all of these still the same width? Yes. So delta x is how wide each one is because it's your change in x. So each x you step over on the x-axis, that's going to give you your new width. These are called left endpoints because where is the rectangle connecting? On the left side. Is this left approximation, would this be an overestimate or an underestimate? Under. What about the right side? Over. An over. Do you think right sides are always over? No. It kind of depends on like which way your curve is going. So just be careful, like left and right are not the same as over and under. It's kind of just based on like what your pictures are doing. The last thing, and this one we're going to draw ourselves, is what if instead of having a right or a left, we want to have a midpoint rectangle. So a midpoint rectangle means where do you think we want our rectangle to hit? In the middle. So we are still going to have our same 4 partitions. And I know yours is kind of light, but it's the same 4 partitions. And instead of making your rectangle so it hits on the left or the right, you go to the middle of your interval, up, and that's where you want it to hit. So it's not a left or a right, it's hitting your curve in the middle. So then here's your interval, you go in the middle, you want it to hit in the middle, and you make it from there. So the style of rectangle just tells you how you want your rectangle to hit your curve. Out of those 3, which one do you think is the best approximation? A midpoint, because it has a little bit over, a little bit under. But at the end of the day, you will usually be told what kind of approximation to use. So you really don't ever have to worry about picking. You'll be told like use a left endpoint or use a right endpoint. We're just going to jump into some problems. So first one we're going to do is right endpoint rectangles, and we're going to use various rectangle styles and 4 sub-intervals to approximate the area under the curve for y equals the square root of x on the closed interval 0 to 4. I am going to show you guys the sigma notation, kind of just to help us get ready for the rest of the week. But all the sigma notation is we have some generic formula, I equals 1, and it's going to go up until n. So this is just saying our base times our height the function value times the width of the rectangle. If we add up all those rectangles, it'll tell us an approximate area. I think it's best to find delta x first. Delta x is always just going to be how wide your rectangle is. It's based off of how long is your interval. So what does our interval run from? 4 to 0. N is the number of partitions. How many do we want? 4. So what is 4 minus 0 over 4? 1. What that means is all of our rectangles are going to have a width of 1. So delta x is the rectangle width. I think pictures are the way to go on this, because when you just start setting this up, okay, 0 to 1, there's going to be a rectangle, 2, 3, 4. Most of the time, your interval should work pretty well with the numbers that you're given. So a right endpoint means when we connect our rectangle, what side wants to touch the function? The right side. So you go to the right side of your interval, up to the curve, over and down. So once you hit it on the right side, you just go over and down and you complete your rectangle. So what that really is saying is we're going to find the sum of all of the rectangles with a height given by the function, the square root, times the width, which is delta x. And this is just counting, saying like, hey, we have 4 rectangles. Do not worry about solving this formula or anything. This is just a like, hey, summation formulas is just telling in a shortcut way, find all your areas and add them up. So, to find all the areas, it is the base times the height summed of all of them. So go just step by step. So in this very first rectangle, what is the base of it? 1. There's your delta x. Delta x is always going to be 1. What number is going to bound our right side? What number? What's our x value on the right side? So isn't it just like times f of 1 plus our next rectangle? What is the width of it? 1 plus what number is bounding its height? 2. So it's f of 2 plus our next rectangle. What is the base of it? 1. What number is bounding the height? 3. So it's f of 3. Last one. 1 plus f of 4. I'm writing it out in the function notation just so you can see like that's all that part of the sum means. It's f of whatever rectangle you're on. Since we have a function, it's the square root of x. What is the height at 1? What's the height at 2? What's the height at 3? Height at 4? Good practice to leave your answers as exact and approximations. The ones obviously aren't doing anything. What's the square root of 1 plus the square root of 4? Square root of 1 is 1, square root of 4 is 2. So as an exact answer, is this going to be our area approximation? Decimal approximation, it is approximately equal to 6.146. When it changes to the left side, and we're just going to go through this whole process again so you can kind of see like, okay, you're given something to do. Step 1, find your delta x. So delta x is b minus a over n. How long is our interval? How long is our interval? 4. How many partitions? 4. What does delta x equal? 1. So what we're really doing is the sum of f of whatever rectangle we're on up to 4 times our delta x. Your lengths are still going to be 1. The difference here, when you connect this on the left side, where is your first rectangle on the left side? 0. The left side of this interval is at 0, so your first rectangle is right there. So then your next rectangle is 1 over. First rectangle has a width of 1. Its height is based off of 0. The second rectangle has a width of 1. Its height is based off of 1. The third rectangle has a width of 1. Its height is based off of 2. Third rectangle, width of 1. Height is based off of 3. So it's really just going back to base times height. Remembering your height is coming off of the function. So how far off is this one from the right side? 2. So then approximation questions on that? Is one approximation necessarily better than the other? Not really. You kind of just do what you're told. The last one, same setup, but now where are we connecting them? In the middle. We still have our intervals of 1. The midpoints are probably the goofiest because when you connect it, like you actually do have to find the midpoint. In this case, it's really nice. What's the middle of 0 and 1? 0.5. There's nothing wrong with building it as you draw your picture. So like your first rectangle has a width of 1, and its height is being determined by which value? 0.5. This is how I generally do it. I draw the rectangles and write the little equation as I go. So then your next rectangle, what's halfway between 1 and 2? 1.5. So you go up to 1.5, make your rectangle. That rectangle, again, has a width of 1. Your delta x will always be the same. What is that guy's height based off of? 1.5. Next one will be based off of 2.5. Last one based off of 3.5. As an exact answer, is there anything else you can do to that? Nope. So exact answer, you can pretty much leave it as soon as you plug in the numbers. Approximate answer, anyone have it? Point. Good. So compared to the left endpoint and the right endpoint, how does the midpoint compare? It's in the middle of them. What a time. Questions on this? All right, would you guys take a couple minutes or so and like plot all of those points? So be careful when you're counting. So this is a 2. So then I would split them in the half and put your 1s in there. Because you notice in your table you have 1, 1.5, 2, 2.5. Don't worry if they're not like perfectly plotted, because we have our table of values to refer back to. This will be the last problem we do. Rectangular partition. Step 1 is you should find your delta x. So in this case, our delta x, our interval, what does it appear our interval is going to run from? 6 to 1. So it should usually be pretty clear, like our table goes from 6 to 1. Like that is the interval we're given. And then how many rectangles are we going to do? 5. So how long is each rectangle going to be? 1. I'm going to do these in 2 different colors. So when we do the right side one, I think it's easiest where first thing I do is I like partition them off on the bottom so every rectangle is 1 long. So 1 to 2. There's going to be 1 base. There's another. So I put my bases in first, because if you're making right side rectangles, there's your bases. Your height, is it going to connect on the left side, the right side, or in the middle? The right side. So for our first rectangle, is it going to follow the 1 point or the 2 point? 2. 2 is on the right. So you go up to 2. So there's our first rectangle. How long is that first rectangle? How long is the first rectangle? What height is it? How do we know it's at 8? Yeah, you have your table. If you draw your rectangles in first, or if you like fill it in with your points, doesn't really matter. The next one will connect to 3. What? It just looks weird because this one's actually connecting on both sides, but like that side doesn't matter. It's just you connect them wherever it hits it. What is the height of your second rectangle? 8 again. What is the height of your third rectangle? 6. Fourth rectangle. Last rectangle. What is 8 plus 8 plus 6 plus 1 plus 6? 29. Good job. So there's your right side. So can you really say if this one's an over or an under? It kind of changes based on the interval you're in, but you are missing that big top piece, so probably a little bit under. To find a midpoint one. So now we're going to do the same thing, but with a midpoint. Am I good for you to erase my work on the side? For the midpoint, will your width at the bottom change? No. So it's still going to be that long. The difference is now when you connect it between 1 and 2, what number is it going to hit at? 1.5. So you go in the middle of it. 1.5. Oh, I really missed that line. But then this is where our second color might come in handy, so you can kind of draw them on each other. So between 2 and 3, it'll hit at 2.5. Height of the first rectangle is now a 4. Height of the second rectangle, 12. Third rectangle, fourth rectangle, last rectangle. What does that all equal? 29. Is that always going to happen? No, you kind of just got to go with it. So don't worry, because it's an approximation, especially something like this where it's going up and down. A left endpoint would probably be different, but just do what you are told. Something that I just realized, all of these examples, what was our delta x? That will not always happen. So whatever your delta x is, you just count that out along the bottom, and then you go from there. Questions on this? All right, for your homework, you will need your own paper, but I printed off the questions.
That one from
All right, on this sheet. So you are given the function, the interval, how many rectangles, which is your n, and then what kind of endpoints to use. So left, right, midpoint. The last two where it says both an over and an under, you look at your picture and then you either, like, an over approximation means you can switch between the left and the right. So this is where things can get interesting. If you have a function like this, an over approximation means your rectangle should always be over. So on this side, what side are they connecting to? The right. Once it starts going on the other side, though, now what side are they connecting to? The left. So if you are told to do a straight over approximation, you just draw your rectangle so they're always over. It's not a left or a right. It's looking at, like, all my rectangles are over. Same thing with an under approximation. You would draw them so they're always under. Does that make sense? Raise your hand if you're going to be gone tomorrow. So tomorrow we're going to do more with this. And then these are all rectangles. We're also going to do a couple examples where instead of making rectangles, we make trapezoids instead. So then you just find the area of each individual trapezoid and add them all up. So I can give you part of the assignment if you're going to be gone tomorrow. I can give you it today before you leave. Also, everyone, tomorrow before school or after school, anyone can come in, get your test, use your notes by yourself, retry any problem that is wrong. If you're gone for music, then you come in Friday morning and do that. So anyone can do that, half points back. You decide what time you need to get here. If you walk in at 7:45, you've just given yourself 10 minutes to do that. So you decide what time you need to be here at, because it's either before school or after school, not half now, half then. Questions about that? Yeah, Peter.